All right, I'd like to thank everyone for making it here at 8 in the morning, and of course the presenters for allowing me to present the work that I've been doing with Arno Lamanak, Justin Cohn, and David Smith about malaria in Swaziland. Also want to take an opportunity to thank my university as well as my funders. So just a very brief recap about Swaziland and malaria. Swaziland, of course, is a very small country in southern Africa, 1.2 million people. Since 1999, they've been trying to eliminate malaria, and they've gone from 2.9 to 0.07 cases per 1,000 individuals, which means they're doing quite a good job. If we look at just the last 4 years, since 2010, there have been a little bit less than 1,400 confirmed cases, and the majority of these have been imported. So if you just do some kind of crude, simple mathematics, it means the transmission potential is much less than 1, just kind of aggregating all the data together. So here we have 0.42. So if you just kind of just naively look at that, it looks like, well, most of the imported cases aren't actually doing much, and there isn't much local transmission. So, you know, we can look at these numbers and say, oh, maybe elimination has either already occurred or it appears to be an inevitability. Now, of course, we've just averaged across all of the data from 2010 on, and that's not quite right. There's a bunch of heterogeneities that might be making sometimes RC would be lower than 0.42, but sometimes it might be bigger than 1. One of these things is there's a significant amount of temporal variation in cases, as one might expect. However, when you look at temporal variation, the story gets a little even better. So here the red is the imported cases per month, the blue is the local cases per month, and you can see if you kind of eyeball it relative to the imported cases, there are fewer local cases as time goes by. So this actually makes it look even better. Again, so we're just looking at these kind of basic numbers of transmission potential. We only have, if you look at the y-axis, sometimes 100 or sometimes even tens of cases a month. So we're still possibly aggregating over heterogeneities that they're going to kind of tell a different story. And unfortunately, the next heterogeneity one could look at, space does start to seem a little bit different. Here, again, red is going to be imported, blue is local, and you can see many of the imported cases occur in the big cities, here and here, but there's quite a few local cases that aren't surrounded by a lot of imported cases. So up here in the north or in the east, there's a lot of blue dots that don't have a lot of red dots corresponding to them. So it's possible that in some places, the transmission potential is quite low, much lower than 0.42, but unfortunately also it's possible that in other places the transmission potential is much higher. And what we really need to understand is how can we go past the simple ratio of local to imported cases to understanding our progress towards elimination. That works really well when you have thousands and thousands of cases, and these little fine points don't matter. But when you really get down to tens or hundreds, it might start making a difference. So put in another way, are we in the scenario here where this looks pretty much like an elimination scenario? We have a lot of imported cases and there isn't much local transmission. There is a lot of local transmission and a raw numbers way of looking at it, but proportional to the total number of imported cases, there isn't much going on. Versus most of the imported cases maybe are happening in the big cities where there isn't much local cases going on, but a few imported cases are causing quite a bit of ongoing transmission, which would tell us that we have not achieved elimination. So what we wanted to do was actually try to figure out how to use the data to infer these arrows, specifically the causal linkages between one case and another case later in time. So the requirements for such a modeling of causality would be we have to account for the movement of both people and the mosquitoes. We want to have this account for mosquito lifespan. Mosquitoes don't live for hundreds of days, so two cases cannot be connected by a mosquito if they're separated by a huge amount of space-time. And we want to be able to say, in this circumstance, does this one particular case look more likely to be caused by that case or that case? Is a case that's closer in space but farther in time more likely than one that's closer in time but farther in space? So we picked actually a relatively simple way of looking at this by having a spatiotemporal kernel of transmission. We use diffusion for movement as kind of a popular, simplest way of thinking about diffusion. We use an exponential distribution for mosquitoes, and then we convolve those two distributions to get some understanding of the relative likelihood of one case versus another causing a third case. So kind of graphically, if we imagine here we have an imported case here, and we go back in time across the x-axis, and then we have distance in the y-axis. The serial interval of malaria makes it so that it's impossible if I got sick today, I can't make you sick tomorrow. So we just shade out the first 30 days. But then from that point on, we have a different probability, or kind of a relative probability, of someone who perhaps was relatively near to where you lived, but got sick 45 days ago, versus someone who lived, let's say, 3 kilometers away from where you lived, but only got sick 35 days ago. And in this particular set for the parameter for the diffusion constant, we would say that the person who lives closer to you but got sick earlier was probably the one that caused your malaria. Not only can we make the judgment call that this appears to be what's going on, but we can also give a relative probability for that link. On the other hand, if we change the diffusion constant, it might turn out that the person who was farther away was more likely to have caused the malaria, because now mosquitoes or people or both can move faster, and so something that is actually closer in time is more likely to have caused it. So we can just move that diffusion constant and assess the relative strength of different linkages. We can also use this method to see what would happen if there's nobody in space-time that is close enough to you to have caused your case of malaria. Now, obviously, malaria can't just magically occur. So what this would be telling us is that there's probably some failure in surveillance, and there should be another person somewhere in here. And so using this method, we can figure out where the most likely places for that person to have been. So kind of quickly going through how we then combine these linkages in time using different diffusion constants. We also acknowledge that if I pick up a case on a particular day, it doesn't mean in all circumstances that that person got sick a fixed amount of time in the past. So if I'm looking at the interval between 2 cases being detected, that doesn't perfectly translate to the interval between 2 people getting infected. So we then move that around a little bit as well. For each set of these diffusion constants and time windows, we get a consensus set of linkages, as well as the strength of those linkages, and then we iterate that process over and over again to try to weight different combinations of diffusion constants and time windows to get one single map that gives us the estimate of the most likely connections. So here, just really quickly, it's kind of hard to see. These green circles are the initiator of a cluster. The green circles aren't all imported cases. Sometimes a local case was an orphan, but then appeared to be the most likely parent of a large set of offspring. Many of the imported cases didn't appear to be most likely to have caused any local case, so there's just a ton that aren't plotted. And you can kind of see this picture that we could have just already seen by just eyeballing the data in space. There seems to be quite a few linkages that are very small. But every once in a while you get a linkage that's quite large, where one case moves into an area where all of a sudden we then have a ton of cases. And this would be a circumstance where if we were able to figure out what was going on with this one case, we possibly could have stopped this entire transmission chain. On the other hand, we have other types of large chains where we have one case that leads to one case, that leads to 2 cases, that leads to 2 cases, and we have these long, branching, ongoing transmission things. Both of these are different. They require different kinds of responses, but they both indicate that there's something going on at the spatial level that you can't see when you just aggregate in time. Specifically, if we then convert this and literally just count the number of linkages that we see, we have, not surprisingly, so these gray dots here are cases that didn't seem to cause any other further transmission. Within the big cities, there's not very much ongoing transmission. And just like we saw before, but now we've kind of quantified, in the north and to the east, there are places where there seems to be quite a bit of transmission potential. We can then, to try to smooth this out across a bunch of ecological, social, and demographic covariates, we can see that different regions of the country are more or less likely to give rise to offspring. Now, this is just saying, if a case shows up there, how many cases would we expect to see? And you can see some places are quite low, like these big cities, and some places are relatively high. That's not really, so if there's a lot of transmission potential, but there's no actual cases ever coming there, that's not telling you much. So the next natural thing to do is to combine that with an understanding of the yearly importation rates. We just literally combine these 2 maps. We get a single map that's able to quantify the expected offspring given all the importation parameters. So this is really kind of a malaria-genic potential of transmission within Swaziland. And again, it tells the same story that we just saw by eyeballing the data, but we can kind of quantify exactly what's going on so we can start making recommendations about how to, now we know that there's something going on, what can we do to recommend how to fix it? So again, just one last time, the cities don't really seem to have much transmission potential. This outer area does have a lot of transmission potential. And by using this map with the other maps, we can look for places where there's a large amount of importation but not too much ongoing transmission potential. So we don't really need to worry about that place as much as a place where there's a lot of importation and a lot of ongoing transmission potential. versus a place where there's not a lot of importation but a huge amount of transmission potential, you would probably treat those two places differently if you were trying to move forward with the elimination effort. So this is exactly the next bit of work we're going to be doing, trying to combine this analysis with an economic analysis and obviously a resource analysis to see how we can stratify the resources available to move farther towards elimination. So one thing that people always kind of think about when they start thinking about these linkages is it would be great to have a genetic component that would be able to connect the recommendations or the linkages that we're saying and really either support them or say that there's actually another story going on to play. This is just a good opportunity to give a shout out to one of our collaborators. Later today, Alex Perkins is going to be presenting a poster specifically talking about this exact thing. So I'd recommend everyone going by. He's trying to infer transition networks by using exactly that kind of data. So also another thing that we're going to be talking about, this is really looking at, given an importation map, what would we expect to see? We'd really like to not have to sit back and wait for the importations to occur. We want to understand where the importations are coming from, and maybe we can get a little bit ahead of things. So one of the other things we're going to be looking at is trying to understand the connectivity between Swaziland and other places in Africa, specifically Mozambique, and see if we can use that to even further improve our recommendations. And then finally, something that I talked about briefly but kind of just let go was that in addition to understanding transmission potential, this model can be used to assess where there were failures in surveillance. So was there systematically in spatiotemporal, was there space-time windows where we systematically seem to have orphans occur more likely or less likely than other places? Because if you're trying to evaluate elimination, you have to try to get all the cases. And if there's places where you're just always missing cases, that'll actually help you understand what's going on. So with that, I'd like to thank you for your attention and ask if there are any questions.
Hi, let me congratulate you on that. It was really fascinating. I'm confused about your assumptions on the diffusion characteristics in the urban area and why it appears that you expect that imported cases are going to lead to less diffusion than they would in the rural areas. Maybe I got that wrong, but...
Oh, no. So the diffusion kernel is assumed to be constant across the country, which actually might not be necessarily true. There might be more connectivity in the urban areas than the rural areas. We're not assuming that it's less in one place versus another. We test a suite of diffusion constants across the whole country. So in one circumstance, we'll say on average, people move a kilometer a week. And then we'll see what kind of connections would be most likely to occur in that circumstance. And then we say, what if on average they move 5 kilometers in a week? And we see which linkages are more or less common than others. Certainly looking at a kind of a gravity-based approach instead of just a simple diffusion-based approach might actually link up some of the cases. But I'd still argue that a lot of the data, just kind of eyeballing, again, I should have put a scale window on this. A lot of it, this is about, let's say, 20 kilometers, the distance of my shaky pointer. So, I mean, these blues are pretty, it doesn't necessarily seem that just a different diffusion constant would say that these blues were being caused by these reds.
Hi, congratulations. I think it's great that you're able to incorporate the heterogeneity of the transmission potential within Swaziland. But I have a few questions. Have you thought about how you can incorporate the asymptomatic infections? Also, has the model been able to predict the cases in, say, 2011, 12, 13, 13, 14? And then just one more question, sorry. I don't understand how there can be a transmission potential in Mbabane and Manzini. I think in the cities, because the RC was 1 in Mbabane and Manzini in some of the major cities. I didn't understand how, because these are maybe in Manzini, but in Mbabane and some of these cities, there's no local transmission.
So
they're all imported cases.
I mean, there's a few tiny little blue dots hiding underneath the red dots. There's a bit. I mean, it's really small relative to the number of red dots. Probably could have made them see-through to be a little bit clearer. You can kind of see it here where there's just a ton of red dots, but there's a little bit of blue dots peeking out. So the transmission potential is much lower there, but when you then adjust that to the amount of imported cases, there's just going to be even if the transmission potential is extremely small, given so many occurrences, one of them is likely to spark something that's going to happen, because it's not simply everyone's going to cause exactly 0.2 cases. It's a kind of a branching process thing where most of them will cause none, a few of them will cause 1, and then there's a very small chance that one will cause a bunch.
Mm-hmm.
going backwards through the questions.
Asymptomatic infections, asymptomatic infections, and predictability.
Right. So.
In the interest of time, in the interest of time, if you could kind of maybe answer one more, and then we'll have to move on, and you can talk later.
Right. So the model itself is not supposed to be predictive. It's supposed to indicate risk. So we're more trying to assess how the process is going. We don't have the kind of climatological variates that should actually make it be a predictive model. As far as asymptomatic cases, that is a great question. That is a problem, and that is one of the things we would hope the genetic data would be able to answer.
Thank you so much.
Thank you, and thanks for all your questions, too. It's great to have good questions. We just have to be able to keep the session on time, too. So afterwards, please feel free to find the speakers.